In this video, we're going to discuss thermodynamics. Thermodynamics is an area of physics that looks at how heat, energy, and work relate to a system. One measurement that we must look at is temperature, which is a property of a system. The Zeroth law of thermodynamics states that if bodies A and B are in thermal equilibrium with body C, in other words at the same temperature, then bodies A and B must also be in equilibrium. So if you have A, C, and B, so if A and B are in thermal equilibrium with body C, meaning they're at the same temperature, then A must be in thermal equilibrium and at the same temperature as B. To measure temperature, we must define a standard reference point and give it a standard temperature. So we use the triple point of water. And that's where water exists as a liquid, a solid, and a vapor. The triple point of water turns out to be 273.16 Kelvin. Now notice I didn't say degrees Kelvin. You don't use the term degrees when you use Kelvin. You can have degrees centigrade and degrees Fahrenheit, but you just have kelvins. And we can convert between the different scales. So the temperature Celsius is equal to temperature Kelvin minus 273.15 degrees. And we're using degrees because Celsius is in degrees. And Fahrenheit temperature is equal to 9/5 times the Celsius temperature plus 32 degrees. So that's how we convert. Now, let's discuss thermal expansion. When heated, solid objects undergo a thermal expansion. This expansion can be calculated. And if we're looking at a linear expansion, for example, a rod, we find that with heat, the change in length of the rod is equal to its original length times the coefficient of linear expansion times the change in temperature. And again, that's the coefficient of linear expansion. This is the change in length. This is the original length. And this is the change in temperature. Now, this is linear expansion. Now, you can have expansion in 3 dimensions, such as a sphere or a block of copper. And we have a volume expansion then. And that's calculated by the change in volume is equal to the initial volume times the coefficient of volume expansion times the change in temperature. That's the coefficient of volume expansion. And one thing to note is that a liquid only undergoes volume expansion. And another thing to note is that water behaves differently. Water from 0 to 4 degrees centigrade, water contracts. And above 4 degrees centigrade, water expands. And this is why ice forms at the top of a lake or a pond. Now let's discuss heat absorption. A system in its environment can exchange heat, usually from a hotter region to a colder region. This is due to a transfer of thermal energy or heat, measured by the value Q. And that's equal to the amount of heat transferred. And it's a form of thermal energy. And Q is measured in joules, or very often in calories, where 1 calorie is equal to 4.19 joules. And we can also use BTUs, which is 3.97 times 10 to the minus 3 BTUs. But we usually use calories and joules. Now, the change in temperature of a system due to the amount of heat it absorbs or loses is related to its heat capacity, C, where Q is equal to C times delta T. And here we're using capital C for heat capacity. And that relates the amount of heat that will cause a temperature change in a system. But a more massive body will absorb more heat than a smaller body. So we can get more specific about heat absorption or loss using the specific heat, which is the heat capacity per unit mass. So in this case, Q is equal to little c times mass times delta T, where little c is the specific heat. Instead of using mass, we can also express the amount of a substance in terms of moles, where 1 mole is equal to 6.02 times 10 to the 23rd atoms or molecules of the substance. In this case, we would use the molar specific heat. And as you will see in future videos, this is Avogadro's number. Now let's talk about heats of transformation. When a solid or liquid absorbs or loses heat, its temperature may not change. Instead, thermal energy may be used for a change of state or phase. For example, when ice melts or water turns to vapor. These are phase changes. Therefore, we must account for this when we look at the heat transfer and the temperature change. We do this through heats of transformation, where Q is equal to Lm, where m is the mass of the object and L is the heat of transformation. And we can be more specific with the heat of transformation. So when you have a phase change from a liquid to a gas, or a gas to a liquid, we use the heat of vaporization. So Q is equal to LVM, where that is the heat of vaporization, going to a gas or back to a liquid. And if we go from a solid to a liquid, or from a liquid back to a solid, we use the heat of fusion, and in that case, Q is equal to L sub F times M, where this is the heat of fusion. So, for example, when water goes from minus 10 degrees centigrade to plus 10 degrees centigrade, it goes through a phase change as heat is added. So from minus 10 degrees centigrade to 0, it's ice, and the ice is absorbing the heat. So we would use an equation such as the specific heat for ice. But once it reaches 0 degrees, it stays at 0 degrees, and it goes through a phase change where it goes from ice to water. Well, the temperature doesn't change, but energy is used to convert it from ice to water. So we would use the energy put in is equal to the heat of fusion times the mass. We would use the heat of fusion equation. Now, once we're at the temperature of water and it heats to 10 degrees, we're again heating up the water, and the heat you would use the specific heat of liquid water times mass times delta T. So we actually have to make 3 calculations when you heat water up from below freezing to above freezing. You have to do a separate calculation for the change of phase, and that will work for any system that melts or vaporizes. Now let's get into the first law of thermodynamics. Okay. This applies the conservation of energy of a system to its heat transfer and mechanical energy, or work. So the first thing we're going to look at is the work the system does. So let's take a gas in a cylinder that has a piston, okay, and you heat up that system with a candle. That gas is going to expand, and it's going to move the piston up a distance. So there's a force pushing up, moving it over a distance, so it does work, and that work is equal to the total of force times distance. Well, in this case, that would be equal to the pressure times the change in volume from initial to final volume. And if dV is equal to 0, then no work is done. Now, when a gas system changes from one state to another through changes in pressure, volume, temperature, etc., the path it takes will affect the work done and the heat transferred. So if you look at your pressure volume diagram, you get systems that can go through all kinds of transformations, and the path it takes from first to second state does matter when it comes to work and heat. However, the quantity of heat minus work does not depend on the path. Q minus W only depends on the initial and final states, not how it got there. So from 1 to 2, although work and heat may vary depending on path, Q minus W does not. So Q minus W defines the internal energy of a system such that the change in the internal energy is equal to Q minus W. And this also can be written as D internal energy equals dQ minus dW. So either one of these is a description of the first law of thermodynamics. And I like to point out that change in internal energy, dE sub int, is also written as delta U in some textbooks. But rather than confusing that with potential energy, I'm using the change in internal energy as delta E sub int to avoid confusion. So as you see from the first law of thermodynamics, heat loss or absorption can change the internal energy. So if Q heat is absorbed, then you get an increase in internal energy. And Q must have been positive. If heat is lost, then you get a decrease in internal energy, and Q is negative. Let's look at the other part of that equation, which is the work done. Now, work can be done by a system or on a system. So let's go back to our cylinder with a piston, and we have gas in it, and we're heating that up with a candle. So as we heat up the gas, the pressure and the temperature increases in the gas, and it expands and it pushes the piston up. So that's moving this piston over a distance with a force, so it's doing work. So this is work done by the system. And in this case, the change in internal energy, which is equal to Q minus W, as we do work, a positive work, as W increases, this term decreases, so therefore the internal energy decreases when work is done by a system. Now let's look at the opposite situation. We have the same system, piston, a gas, but instead of heating it up, we're compressing the gas, pushing down on the piston, and that is causing the gas to compress, the pressure to go up, the temperature will probably go up. So this is work done on the system. So the change in internal energy is equal to Q minus W, but this is considered a negative work. And when we add a negative to this negative, this becomes more positive, so this actually increases, and therefore our internal energy increases. So when work is done on a system, the internal energy increases, whereas when work is done by a system, the internal energy decreases. And some textbooks will write it as this: the change in internal energy is equal to Q minus W, where the work is done by the system, or delta change in internal energy is equal to Q plus work done on a system. But this is the same thing. When work is done on a system, you're adding negative work, which increases internal energy. So let's summarize. The internal energy will increase if heat is absorbed, or work is done on the system. And internal energy will decrease if heat is lost or work is done by the system. Now let's discuss types of thermodynamic processes. So we use thermodynamics for a number of different reasons. It's used to develop power in your car engine or in a steam engine. We use it in a kiln or oven to heat things up. And there are different ways that you can do that. So the different processes that a system can undergo are: the first one is adiabatic. And in this case, there's no transfer of heat. This can occur if the change in the system is very rapid or the system is well insulated. So since internal energy is equal to Q minus W, if Q is 0, then we get the change in internal energy is equal to the work done. And if you do positive work done by the system, internal energy goes down. And if you have work done on the system, internal energy goes up. Another type of process is isochoric, or constant volume. And in this case, the change in volume is 0. Therefore, the work done is 0. Of course, you need to have a change in volume to have work done, and our change in internal energy will be equal to just the heat transfer in or out. A third one is cyclical, where the system returns to its initial state. In this case, since it goes back to its initial state, the change in internal energy equals 0, then Q equals W, and the net work done is equal to the transfer of heat. Another process is called free expansion. And in this case, the system expands into an unrestrained volume, such as a vacuum. There's no heat transfer and no work done with the environment. Therefore, heat and work is equal to 0. And the change in internal energy is therefore 0. Another process is an isolated process, where the system has no interaction with its environment. In this case, no heat is exchanged and no work is done. Another one is an isobaric process. And with that, there's no change in pressure. And there's also an isothermal process where there's no change in temperature. Now let's look at the mechanisms of heat transfer. The way that heat actually moves from one system or body to another. The first way is conduction. And with conduction, you get a transfer of heat and energy from atom to atom in a body or between bodies. So if you have a metal rod and you heat one end, the heat is conducted or transferred through the atoms of the rod. And we configure a conduction rate, and the conduction rate, P conduction, is equal to the amount of heat transferred per unit time, which is equal to K A times TH minus TC over L, where K is the thermal conductivity, and thermal conductivity is measured in watts per meter Kelvin. A is the area of the body, and TH and TC are the hot and cold temperatures from one side of the body to the other, and L is the thickness of the body. And actually, the change in temperature over L is the temperature gradient of that body. Now, I also want to point out that the conduction rate that I've written as P sub COND is also written as H in many textbooks. So these are the same things, the conduction rate of heat in a body. Now you can also have resistance to conductivity. That's what insulators do. They resist the transfer of heat, and we call that thermal resistance, and we give it an R value, where R is equal to L over K. And you may see this R value listed on insulation when you go to a home supply store. Now, if you have a number of insulators between two bodies, you can still measure the total conductivity between A and B as A times the hot and the cold temperature, if this is hot and this is cold, divided by the sum of the resistance. You just add up the sum of L over K for each insulator between the bodies. Now let's look at another mechanism of heat transfer, and that would be convection. Convection occurs when a fluid, such as water or air, is heated, then the fluid changes density and moves around, bringing the heat to other areas of the fluid. So if you have a beaker filled with water and you heat that, you get currents of the fluid moving, and that is convection, where the heat is transferred to the rest of the fluid. Let's look at the third way energy can be transferred. That is through radiation, and that uses electromagnetic radiation or waves, such as light. And that requires no medium. That is why the sun can transfer its energy to the earth through a vacuum. Now, we can measure the rate of transfer of energy, in this case, the rate of radiation, and that's equal to sigma epsilon A times T to the fourth, where sigma is equal to the Stefan-Boltzmann constant, which is actually equal to 5.67 times 10 to the minus eighth watts per meter squared per Kelvin to the fourth. And epsilon is the emissivity constant of the object, and that usually varies from 0 to 1. A is the area that the radiation falls on, and T is a temperature in kelvins. Now, I'd like to point out also that when I use P sub rad and P sub absorption for rate of radiation and absorption of energy, some textbooks will again use H for that, but it's the same thing. Now, an object can radiate and absorb radiation, and the rate of absorption is given as sigma epsilon A times T of the environment to the fourth, where that's the temperature of the environment that the object is absorbing energy from. And objects can radiate and absorb energy at the same time. So you can get a net rate of absorption or radiation, P net, which is equal to P absorption minus P radiation, which comes to sigma epsilon A times T of the environment to the fourth minus T to the fourth. Let's do some problems in thermodynamics. Here's the first one. A 20-meter long train rail is attached to the track at its ends. As the day progresses, the temperature of the rail increases by 25 degrees Celsius, causing the rail to buckle in the center. How high does the center of the rail raise up? And the linear expansion coefficient for steel is shown. So let's make a little bit of a diagram. Here's our rail, and we'll assume that as the day progresses, it heats up and it buckles in the center a distance y. And we're going to call the original distance of 20 meters, we're going to call that 2x. So that's x and that's x. And if the rail buckles, then this distance will be x plus delta x. Now, we know from linear expansion that the change in the length is equal to L times alpha times delta t. In this case, we're using x, so for us, the change in x will be equal to x times alpha times the change in temperature. So let's go back to our diagram. The Pythagorean theorem says that x squared plus y squared is equal to x plus delta x squared. Or if we solve for y squared, that's equal to x plus delta x squared minus x squared. And therefore y will be equal to the square root of x plus delta x squared minus x squared. And if you multiply x plus delta x times x plus delta x, and you subtract x squared, this becomes the square root of 2x times delta x plus delta x squared. Now, we're going to make an assumption. We're going to assume that delta x, that little bit of increase in the track length, is much smaller than the actual track length itself. So we're going to say that that goes to 0 and y becomes the square root of 2x times delta x. Now, we also found that delta x is given by the equation for linear expansion. So this becomes 2x times x alpha change in temperature square root, or square root of 2x squared alpha delta t. And if we put in these numbers, x is 10 because 2x is 20. So that's 2 times 10 squared times alpha, which is given as 12 times 10 to the minus 6, times the change in temperature, and we were told the temperature raises by 25 degrees. And if you carry out that math, you get y is equal to the square root of 6 times 10 to the minus 2, or it's equal to 0.245 meters, or y is equal to 24.5 centimeters. That is the height the center of the track rises to due to expansion. Here's another problem. 3 liquids of the same mass, designated as A, B, and C, have temperatures equal to 12, 18, and 28 degrees Celsius respectively. When A and B are mixed, the mixture comes to a temperature of 16 degrees. When B and C are mixed, the mixture comes to a temperature of 23 degrees. What temperature would a mixture of A and B come to? Okay, so let's describe this in a picture. You have 3 liquids. You have mass A, mass B, and mass C of these liquids, and we're told they're all equal. And A is at 12 degrees centigrade, B is at 18 degrees centigrade, and C is at 28 degrees centigrade. So when we mix A plus B, we end up with 16 degrees centigrade. When we mix B plus C, we end up with 23 degrees centigrade. And we want to know what we end up with if we mix A plus C. What's the equilibrium temperature? So we're going to use specific heats. And we know that in a system, the heat lost by the hotter system is equal to the heat gained by the cooler system. So let's look at each of these systems. So first we'll do when we mix A and B. So for the mixture of A plus B, we say, and we know that the heat transferred is equal to mass times specific heat times change in temperature. So for A plus B, we know that the heat transferred is equal to the mass of A times specific heat of A times the change in temperature of A, and A goes from 12 to 16 degrees, so the change is 12, we use 16 minus 12, and that has to equal the mass of B times the specific heat of B times the change temperature of B, which went from 18 to 16. So we know the mass of A and the mass of B is the same. So specific heat of A times 4 is equal to specific heat of B times 2, or we get specific heat of B is equal to 2 times the specific heat of A. Now let's do the same thing for the second mixture we're given, which is B plus C. So again, the mass of B times the specific heat of B times the change in temperature, and B is going from 18 to 23, so that difference is 23 minus 18 is equal to the mass of C times the specific heat of C times the difference in temperature, which is 28 minus 23. Again, the masses are equal, so we get specific heat of B times 5 is equal to specific heat of C times 5, or specific heat of B is equal to the specific heat of C, which is equal to 2 times the specific heat of A. Of course, we found that up here. Now, let's go to our third system, which is the unknown. This is for A plus C. And going through that again, the mass of A times the specific heat of A times the difference in temperature. Well, in this case, we're going to call the temperature that the system comes to T. So, because C is warmer than A, we know that A is going to warm up. So this will become T minus 12, the initial temperature of A, and that has to equal the mass of C times the specific heat of C times the temperature. In this case, it will be 28 minus T. And again, these masses are the same, and we get specific heat of A times T minus 12 is equal to the specific heat of C times 28 minus T. However, we know that the specific heat of C is equal to 2 times the specific heat of A. So specific heat of A times T minus 12 is equal to 2 times the specific heat of A times 28 minus T. Or these cancel out and get T minus 12 is equal to 56 minus T minus 2T, or 3T is equal to 68. T is equal to 22.7 degrees Celsius. So this is the final temperature we get when we mix A plus C. Here's our next problem. A bullet with a mass of 3 grams is shot into a block of wood weighing 50 grams at a speed of 100 meters per second. If the block cannot move, how much does the temperature of the bullet increase? If the block is able to move, how much does the temperature of the bullet increase in this case? And the specific heat for the lead bullet is given as 0.03 calories per gram degrees Celsius. So let's diagram what's happening here. We have a bullet that's being shot into a block of wood, and the bullet weighs 3 grams. The block of wood weighs 50 grams, and this is moving at 100 meters per second. And we're given C for the bullet is equal to 0.03 calories per gram degree centigrade. So in the first case, the block doesn't move. So when the bullet flies into the wood block, all the energy that the bullet has in it, which is kinetic energy, is transferred to the block in the form of heat. So we know the kinetic energy of the bullet is equal to 1/2 mv squared, where v is the velocity of the bullet, and that's equal to the heat transfer from the bullet. And that would be equal to 1/2 times the mass, which is 3 times 10 to the minus 3 kilograms, times v squared, which is 100 meters per second squared. So the kinetic energy of the bullet, which is the energy in the form of heat, ends up being 15 joules if you make that calculation, which, if we convert it to calories, that's 3.58 calories. And I'm doing that because our specific heat is given in calories. So we know that Q is equal to mass times specific heat times change in temperature. And so we're looking for the change in temperature of the bullet. So if we solve for delta T, that's equal to Q over mass times specific heat. So we can substitute these values in to get the change in temperature of the bullet. So Q is equal to 3.58 calories over the mass, which is 3 grams, times specific heat, which is 0.03 calories per gram degree centigrade, which then becomes 39.8 degrees centigrade. And this is the increase in the temperature of the bullet due to hitting the block. Now in the second part, we want to know what the temperature increase of the bullet would be if the block is free to move. So we have a system where you have the bullet and the block, and then we end up with the bullet embedded into the block and both moving. So this is mass m, mass big M, and this mass of this system is m plus little m. So we can use conservation of energy and conservation of momentum to work out this problem. Also note that some of the kinetic energy that the bullet initially had goes into the kinetic energy of the bullet and block system and is lost to heat. So the bullet will not heat up as much because some of the initial energy is lost to the kinetic energy of the final system. So if we use conservation of energy, 1/2 mv squared, which is the initial energy of the bullet, the initial velocity of the bullet, is equal to 1 half mv1 squared, which is the final velocity of the bullet, plus 1 half big M v1 squared, which is the final velocity of the block of mass, big M. So that's conservation of energy. But we also have conservation of momentum. So the momentum of the bullet initially has to equal the momentum of the final system, which is the total mass of the block and bullet times v1. So this is conservation of momentum. So if we take this equation and solve for v1, we get v1 is equal to mv over big M plus M. And now we can go back and solve for a change in temperature. So initially, when the block didn't move, we said that the heat energy that goes into the bullet is equal to the initial kinetic energy. Well, in this case, the heat that goes into the bullet is equal to the initial kinetic energy, but some of that energy is lost to the kinetic energy of moving the system. So we have to subtract that. So that's minus 1 half the total mass of the final system times v1 squared. So that becomes 1 half mv squared minus 1 half m big M plus little m times v1 squared we found up here. So this is little m over v times big M plus m squared, which becomes 1 half mv squared minus 1 half m plus little m times m squared v squared over m plus little m squared. Well, one of these cancels out, and we end up with 1 half mv squared minus 1 half m squared v squared over big M plus little m. Well, we can take 1 half mv squared out. 1 half mv squared times 1 minus m over big M plus little m. These equations are similar. And if we combined these terms with the most common denominator, this becomes big M plus little m minus little m over big M plus little m. Everybody has to remember their algebra, which is 1 half mv squared. These cancel out. Big M over big M plus little m. And we can put these numbers in. 1 half mass of the bullet is 3 times 10 to the minus 3 kilograms times v squared, which was 100 meters per second squared, times big M, which is 50, over big M plus little m, which is 3 grams. But this ends up being a ratio, so the units don't matter, which if you do the calculations, this comes out to be 14.2 joules, which is equal to 3.4 calories. And once again, we can find the change in temperature by using Q over mass times specific heat, which is 3.4 over 3 grams times 0.03 calories per gram degree centigrade. Okay, and we're using 3 grams because calories is per gram, and this becomes 37.8 degrees centigrade. So that's the temperature the bullet goes up when the block moves, which as you can see is less than it goes up when the block is fixed because it loses some of this energy to the kinetic energy of the block. Let's do another problem. What is the work done and change in internal energy for a 6 centimeter cube of copper that is heated from 20 to 320 degrees Celsius? And the specific heat and volume expansion coefficient is given for copper. The mass of the copper cube is 1,800 grams. So we want to find the change in internal energy so that we know that's equal to the Q, the heat, minus the work. So we have to find those values. So we know that Q is equal to the specific heat of the metal times the mass of the metal times the change in temperature. So we can put those values in. That's equal to 0.386 joules per gram degree centigrade times 1,800 grams, the weight, the mass of the cube, times the change in temperature, 300 degrees Celsius. And that becomes 208,440 joules. So now we have Q. Now we want to find the work. Well, the work is due to the volume expansion because work is equal to the pressure times the change in volume. So we now have to find the change in volume. So we know that the volume expansion is equal to initial volume times beta times delta T, which is equal to, well, the volume of the cube is equal to 6 cubed, which is 216 centimeters cubed. So that's equal to 216 times 10 to the minus 6 meters cubed times beta, which we were given as 51 times 10 to the minus 6th per degree Celsius times the change in temperature, which is 300 degrees Celsius. And that comes out to be 3.3 times 10 to the minus 6 meters cubed. That's the change in volume of the cube due to heating. So we're also going to assume that pressure is going to be standard atmospheric pressure, which is 1 times 10 to the 5th pascals. And a pascal, if you recall, is a Newton meter squared. So our work is equal to pressure times the change in volume, which is 1 times 10 to the 5th pascals, or Newton meter squared, times 3.3 times 10 to the minus 6 meters cubed, which gives us 0.33 Newton meters, or joules. So our change in internal energy is equal to Q minus W, which we found Q up here, which is 208,440 joules, 208,440 joules, minus the work, which is 0.33 joules. Now, 0.33 is minuscule compared to the 208,000, so we're going to ignore that, call that 0. So our change in internal energy is approximately 208,440 joules. And what you can note from this is that when you have a solid and even a liquid that expands, most of the change in internal energy is due to the heat transfer. Very little of it is due to the very small amount of work done by the expansion. Here's another problem. A block of ice is pressing against a copper rod with a radius of 1 centimeter, length 20 centimeters, and thermal conductivity K equals 90. The end of the copper rod opposite the block of ice is at 100 degrees centigrade. How long it will take to melt 40 grams of ice due to the heat from the copper rod? For ice, the heat of fusion is equal to 8 times 10 to the fourth calories per kilogram. So we can diagram this. We have a copper rod, and the rod has a radius of 1 centimeter. And this is the block of ice. The block of ice is 40 grams. The rod is 20 centimeters long. Here's ice. Here's our rod. And this end of the rod is at 100 degrees Celsius. So we want to know how long it will take to melt the ice due to the heat coming up from the rod. Well, the conduction of heat is given as the amount of heat transferred per unit time, which is equal to K, the thermal conductivity, times area, times the hot temperature minus the cold temperature over the length of the rod. So we can put the values in for that. So peak conduction is equal to K, which is 90, times the area of the rod, which is 0.01 meters squared, times pi. So we can put these numbers in. Peak conduction is equal to K, which is 90, times the area of the rod, which is pi r squared, or pi times 0.01 meters squared, over the length of the rod, which is 0.2 meters, times the hot minus the cold temperature. So ice is at 0 degrees. So the hot minus the cold temperature is 100 minus 0. So that becomes 90 times 3.14 times 0.01 squared over 0.2 times 100, and this comes to 14.1 joules per second. That's the amount of heat being transferred through the rod. Now that we know the conductivity, which is the rate of heat transfer per second, we can use that to find the time it takes to melt the ice. So we can use the heat of fusion to do that. So the amount of heat transferred is equal to the heat of fusion times the mass. And we know the heat of fusion, that's 8 times 10 to the fourth calories per kilogram. And the mass is 0.04 kilograms. So the heat transferred is equal to 3,200 calories, or 13,408 joules. So we know that the conductivity, which is heat per unit time, is Q over T, and we're looking for time. Therefore, time will be equal to Q over P conductivity. So time is equal to Q, which is 13,408 joules, over conductivity, which we found to be 14.1 joules per second. So the time it takes to melt the ice is 951 seconds, or 15.8 minutes. Let's do one more problem. A window assembly consists of a double pane glass window separated by an air space. The glass is 60 by 60 by 0.3 centimeters. The air space is 0.3 centimeters wide. The inside temperature is 20 degrees Celsius and the outside temperature is 0 degrees Celsius. What is the rate of heat transfer per second through the window? For air, thermal conductivity, K equals 2 times 10 to the minus fourth calories per second per centimeter. And for glass, K is equal to 2 times 10 to the minus third. So you can see a drawing of this window system. You have glass 1 and glass 2 separated by an air space. The inside temperature is 20 degrees Celsius, the outside is 0 degrees. And each segment is 0.3 centimeters wide. And I put here the temperature of the interfaces. So the temperature of the surface of the inside of the glass is 20 degrees centigrade. So T1 is equal to 20 degrees Celsius. T2 and T3 are the temperatures at the interface of the air with the glass, and T4 is equal to the temperature of the glass on the outside, which is 0 degrees Celsius. Now we know that the conductivity is equal to K, the thermal conductivity, times the area times the hot temperature minus the cold temperature over the length. So let's look at each of these segments, and we'll call the first one the conductivity of glass 1 segment. So we'll put the numbers in. That's equal to K, which is 2 times 10 to the minus 3 for glass, times the area, which is 60 by 60 square centimeters, or 3,600 centimeters squared, times the hot minus cold temperature. Well, the hot temperature is 20 degrees centigrade. We don't know what the cold temperature is. We called it T2. So that would be 20 minus T2 over the length, which is 0.3 centimeters. So if you work that out, you get 24 times 20 minus T2 calories per second. Now let's do the same for the conductivity of air. That's equal to the K for air, which is 2 times 10 to the minus fourth, times the area, which is 3,600 centimeters squared, times the temperature difference, which in this case is T2 minus T3, over the length, which is 0.3. And if you work that out, you get 2.4 times T2 minus T3. And now let's do it for the second section of glass. So that's equal to 2 times 10 to the minus 3 times 3,600, the area, times, and in this case, the difference in temperature is T3 to T4, but T4 is 0. So this is T3 minus 0, which ends up becoming 24 times T3. So now we know our conductivity through our 3 sections. And we know that the conductivity has to be the same through all of them. In other words, Pg1 has to equal P of air, has to equal the conductivity of Pg2. So let's put these down. Pg1 is 24 times 20 minus T2 has to equal 2.4 times T2 minus T3 has to equal 24 T3. And let's divide it all by 2.4. We get 10 times 20 minus T2 equals 1 times T2 minus T3 equals 10 times T3. So if you look at this equation, we get T2 is equal to 11 T3. And if we take this equation, okay, we have 10 times 20 minus T2 is equal to 10 times T3. The 10's cancel out. We get 20 minus T2 is equal to T3. But notice we said that T2 is equal to 11 T3. So 20 minus 11 T3 is equal to T3, or 20 is equal to 12 T3, or T3 is equal to 1.67 degrees Celsius. And if we put that into this equation, T2 comes out to be 11 times T3, which is 18.4 degrees Celsius. So now we have T1 is equal to 20 degrees Celsius, the inside temperature. T2 is equal to 18.4 degrees Celsius. T3 is equal to 1.67 degrees Celsius. And T4, which is the outside temperature, is equal to 0 degrees Celsius. Now, we still haven't figured out what the conductivity is. And we do know that the conductivity through the first section of glass is the same as the conductivity through air, which is the same as the conductivity through the second section of glass. So the easiest one to use is through the second section of glass, because we found that that's equal to 24 times T3. So the conductivity through Pg2 is 24 times T3, which is equal to the overall conductivity. So that's equal to 24 times 1.67 degrees Celsius, or our conductivity is equal to 440.1 calories per second.